Okay, hello again. Thank you again for being here. Let's start with this last microlearning of the year. I'm here with my colleague Raul Ramos from the project department. And we are talking today about ventilation systems for explosive atmospheres. We are reviewing the main consideration for design and calculation for the declassification of these locations to reduce the risks of explosions. As always, a little bit of housekeeping of these sessions. You have in the panel control a tab to write down all the questions you have, and at the end of the session we are answering. We will have a Q&A time, and as always, I'm sharing with you the presentation in PDF. Also at the end of the session. So that's all from my part. Raul, the floor is yours.
Thank you, Carlos, for introducing me. So I'm doing this microlearning about the design and calculation to declassify the locations for explosive atmospheres according to the standard 60079 part 10.1. And this is the table of contents of I will show you. First of all, I will explain about what an ATEX zone is. Then I'll tell about how they are formatted and how they are classified. Following this, I show you how to declassify all the ATEX zones by different variables. And then I'll tell you how to design, how to calculate the required airflow for obtain a proper dilution of the contaminants, and also how to do the equipment selection for this type of areas. But first of all, I want to show you different accidents happened in the past that occurred in the past. So the first one in the left hand of the slide is an accident occurred in a plant in Tarragona, Spain, that produced ethylene oxide, and one of the tanks exploded, causing three people were killed, two inside the factory, one hit by a projectile, and the economic losses of this accident rose up to 5 million euros. On the right side of we have a large explosion occurred in 2008 in USA in a Showa refinery, where there was a lot of concentration of dust and combined with heat that caused a huge explosion, causing 14 deaths and losses about $15 million. Why I explain this? Because they are linked about their caused in explosive atmosphere zones. And what is an explosive atmosphere zone, an ATEX zone? What is this? So it's an enclosed area where flammable gas or dust accumulates, which under normal conditions can cause an explosion depending on its concentration in the air, which can release a lot of energy instantly. And
sorry, Raul.
Yes.
Please get closer to the microphone, because I think we are having a problem with the audio.
Okay. Yeah. Now, do you hear me?
I think it's better. Yeah.
Okay. Okay. Sorry.
Position, but I think it's better for the audio.
Okay. Okay.
Yeah, much better.
Okay, now better. Okay. So I was saying, an ATEX zone is an enclosed area where flammable gas or dust is accumulating, and in which under normal conditions can cause an explosion depending on its concentration in the air, releasing out of energy instantly. And all such areas are indicated with the hazard sign of which you can see here, with a yellow triangle and the letters EX on capital letters. Also, to understand how an explosive atmosphere is formed, we must take into account various environmental factors, which are shown in the explosion pentagon here on the right side. It has a quite analogy with the fire triangle. It's more known, which consists that you need a fuel, as for example gasoline, oxygen as oxidized, and heat, for example, a spark or increase of temperature to obtain a pole fire. And in the case of an explosion, you need two additional factors. One of these is that the space should be confined, enclosed, not outdoors, and also a mixture between the fuel and the air. And all these 5 elements occurring at the same time, that brings you to an explosion event. We also should know about the different parameters of explosivity of compounds. The first one is the flash point, which is the minimum temperature at which a liquid gives off a quantity of vapors that can form a flammable mixture. Then we have the flammability limits, which are the range of concentrations in the air in which we can form an explosive atmosphere. And they have 2 different limits, the lower limit and the upper limit. And then the last parameter is the ignition sensitivity that are defined by 2 subparameters, which are the minimum ignition energy, which is the minimum energy what you need to initiate a combustion. And then the auto ignition temperature, which is the temperature at which a flammable gas mixed with air can ignite spontaneously. Then, to know where an ATEX zone can be formed, when we stay in an ATEX zone, we should know where it's formed. So we have areas where flammable liquids or combustible dust are handled in an industry. Then we have also this type of ATEX zones in manual vapor transfers. Also in inside process equipment like batteries in electronic equipment, storage tanks, also leaks in seals or valves. And then these ATEX zones have 3 different classifications. The most hazardous is the zone 0 or zone 20, sorry, in dusts, that indicates that we are in a continuous and frequent hazard. And it brings us to not use electric motors due to the spark risk. So in that zones, we must use pneumatic motors, for example. Then the following zone is the zone 1, where probable hazard normal where we have a probable hazard or it's likely normal operating conditions. And then you have the zone 2 or 22 for dust, which is what you have on a caution risk and not likely in normal operating conditions. Then, sorry. Oops, sorry. I don't know what happened.
We are watching your desktop.
I'm sorry. I don't know what happened now. Sorry.
Yeah, don't worry, Raul. Just open, please, the PowerPoint.
Yes. Now you can see it.
Yeah.
Sorry.
Yeah, it's the life problems. Don't worry.
Yeah. Okay. So we have here sorry. Then once we have classified these ATEX zones, then we should know about the ventilation availability. Sorry. No.
Yeah, you miss a.
Yeah. I don't. Yeah. Here. Sorry.
Yeah.
Problems of the.
Yeah, don't worry. Happens always.
Okay. So once we have classified the ATEX zones, we need to declassify it to lower the risk. So we have 3 values to take into account and that I will explain in more detail. These are the rate of release, the ventilation effectiveness, and its availability. Then we have the rate of release, which can be continuous, primary, or secondary. In case of a continuous release, that's expected to occur frequently or over long periods. What is this? For example, when we have a tank full of gasoline, its surface should, with a permanent ventilation, will emanate vapors constantly. Then we have the primary release, which is expected to cool periodically or during normal operation, and we can find it in seals of pumps, compressors, or valves with leaks or releases during normal operation. And the secondary release is the one that's not expected during normal operation, but when it happens, it's only for short periods. About the second parameter, which is the ventilation effectiveness, we have 3 grades of dilution. The most desired in this case is the high dilution, where the concentration near the source is reduced abruptly under the lower flammability level in all the cases. Then we have the medium dilution, where the concentration is controlled and providing a stable boundary zone where the leak is occurring. It means that even maybe we are over the lower limit, this concentration is controlled up to not increase the risk. And then we have the low dilution, that is where we have a significant concentration where the leak is occurring, and this concentration persists even when the leak stops. In this graph, from the standard 60/79/10.1, we have a logarithmical graph where we have the characteristics of the release, the volumetric release in cubic meters per second, the x-axis, and then the ventilation velocity in meters per second in the y-axis. So our intention here is to establish over the blue line, which indicates we are in high dilution, to lower the risk and minimize the effect of being in a zone. And the third variable important to mention here is the ventilation availability, which consists on 3 different levels. You have the good ventilation, the good availability, when ventilation is present continuously. Then we have the fair ventilation, that's the one that is expected in normal operation. And then we have the poor ventilation, that's the ones that not meet even the fair or the good standard. So with all these 3 variables, we can stabilize a table. It comes from the standard that indicates in which zone we are depending on these 3 variables. Our intention always is establish a high dilution and a good availability. Why? Because even regardless of the rate of release, if we obtain of those variables high and good, we can establish a non-hazardous ATEX area. So we can put the standard equipment, conventional equipment, non-ATEX one, so we can reduce costs. Otherwise, if we don't have a good ventilation nor high dilution of the contaminants, we would be in an ATEX area, so we need special equipment. Now, for the design and calculation of the minimum airflow, we must know the different formulas that comes from the standard. The first one is the evaporation rate, the evaporation leakage rate, the release rate, which is determined by the pore surface area, the vapor pressure, the wind velocity, the molecular weight of the contaminant or the compound, and also the temperature of the room. And this evaporation rate is in kilogram by second. If we divide it by the vapor density, we will obtain the volumetric evaporation rate in cubic meter per second. And then with this value of volumetric evaporation rate, we can calculate the theoretical minimum ventilation airflow, which depends on the previous variable, the lower flammability limit of the compound, and the room temperature. And it will be divided by 293 Kelvin, which is 20 degrees Celsius. So we have here an example of a benzene leak, which have this have these properties, a low raw material for 1.3%, this molecular weight, and this vapor pressure at 20 degrees Celsius. And we have made an example with an aeration pool, quite simple. A surface area of 1 square meter and a wind velocity of 1 meters per second, and also a room temperature of 30 degrees. Well, having these two formulas, when we plug all these values in both formulas, first we have the release leak, the leakage rate of the compound, and then with this we can calculate the minimum airflow necessary to dilute it. This is a minimum value, so we can approach it or having more airflow or more wind or more ventilation velocity to obtain a high dilution as we desire. But last but not the least, we have the equipment selection, which I think is the most tricky part of this learning. Why? Because it's important to understand the scope of ventilation according to different groups. Here we have two different markings that are in all ATEX equipment. First of all, we have the ATEX marking, which is as per directive of the European Union number 2014/34. And then we have the EN marking that we provide by the standard. So in the ATEX marking, we have for one side the group of electrical equipment, which is divided into groups. The group 1, which is for underground work and mines, which is divided in two categories of very high protection or high protection. And then we have the group 2, which is our interest, because it relates to other risk areas. For example, which is more common for us, for example, in warehouses. Then for group 2, the level of protection is divided in two different groups. We have the category 1 for very high protection equipment that it will be used in zone zeros or lower risk. Then category 2 for the high protection equipment, and they are used for zone 1 or zone 2. And then we have the category 3, which is a normal protection for zone, and it can only be used in zones 2. They have also another letter, a G or a D, depending for the gas or dust respectively. Then we have to know also the explosion groups and the temperature class. This is for the EN marking. First of all, we have the explosion groups, which are 3. The first one is the group 4 mine, the group 1, which are not is not important for us. Then we have the group 2, the gases, and the group 3, the dust for dust. For the group 2, they are subdivided in three levels, from highest to lowest ignition energy. Will be from less risk to higher risk. It is the groups 2A, 2B, and 2C. And for that, we also have 3 different levels. The level A, we don't use it, it's for combustible dust. But then we have the group 3B for conductive dust and 3C for non-conductive dust. Then we have the temperature class regarding the ignition temperature. It goes from T1 to T6. The T1 is the less restrictive class, as it involves compounds that ignite at temperatures higher than 450 degrees Celsius. Then the group T6 is the more restrictive because it goes for compounds with ignition temperatures of 85 degrees Celsius. Then we have here a table which classifies the different chemical compounds regarding its temperature class and its explosion group. It's important to clarify that we cannot manufacture fans to work in ATEX areas with group 2C gas, acetylene and carbon sulfide. But with detergent, yes, because of its very high ignition temperature, which is over 500 degrees Celsius. For these cases, we use the marking 2B plus hydrogen, H2, for all the fans suitable for hydrogen. Then moving forward to the category and explosion protection level, or the EN marking in this case, we have this analogy with the ATEX marking we saw 3 slides before. So we have here the letter G and D, and then a secondary letter, in this case A, B, or C. The line is for very high, high, or normal protection. And here we have the most tricky part of the equipment selection, which is the type of protection the equipment has. You can see different types of protection: flame-proof enclosure, pressurized enclosure, intrinsic safety, encapsulation, safety, etc. And all these protections have its own marking with different letters you can see, P, D, B, I, M, and its own part of the standard. For our case, for SODECA fans, for standard SODECA ATEX fans, for gases we use flame-proof enclosure, the marking D, and increases safety, the marking E, which are, what are them? So the flame-proof enclosure indicates that we have a enclosure that protects the equipment from an explosion, so they cannot explode when an explosion can occur. And all this type of how to do this enclosure is written in the part 1 of this standard. Then we have the increased safety, or letter E, and established in the part 7 of the standard, which indicates that the equipment by itself cannot make electrical arches or having overpressure, overheating inside, and they can obtain it by having a very good electrical insulation with rating at least of IP54. So after seeing the different types of different parts of the marking, here we have the two markings, the ATEX marking and the EN marking. What we can read in an ATEX marking. First of all, we have the marking C. That means that the product can comply with the European requirements. Then we have the identification of the certifying body. Then the marking C for ATEX products, which is this logo I showed you, but I didn't tell you in previous slides. Then the electrical equipment group, which is group 1 for mines, group 2 for the rest. The equipment category, 1, 2, or 3, and if it's for gas or for dust. In the case of an EN marking, we have the explosion-proof device with the letter VX, the type of protection we saw in the slide before, the group of explosion, which is 1, 2, or 3, 1 for mines, 2 for 2 for gases, and 3 for dust. Then the group A, B, or C. Then the temperature class is from T1 to T6, and the explosion protection level will be the letter G or D, depending if it's for gas or for dust, and there's A, B, or C. We are in a category 2 equipment. We'll show this equipment a letter B, meaning that it's a high protected equipment. And then the solutions that SODECA can provide for these cases are the anti-spark fans driven by electric motors, such as the ACDF, it's a special fan for ATEX, and also we have conventional fans like the AC, BF, DCT, and also temperature rated fans like the CJTHT that can be modeled for working in ATEX zones. And they have different types of products depending on they have to work for gases or for dust, regarding the level of protection, the level of category, and the type of protection they need. So to sum up here, this microlearning, I told you that we have a department of projects that which I belong, that can make all the projects that you need and make your project according to your requirements. We made it by our software called QuickFan, where we can do here the calculations of the equipment selection that suits better for your projects. Also have 3D models and BIM for funds for more than 5,000 funds. That then you can download them and then you plot them in on your projects. And don't forget to follow us on LinkedIn to don't lose any of our latest news. So that's the end for the presentation, and thank you so much for attending it. And if you have any requirement or any questions, we are welcome to answer it.
Thank you, Raul, for the nice presentation. Take a sip of water if you want, and in the meantime, I am.
Thank you.
Let the last slide so people can.
Oh yes, sorry.
Can see your email.
Sorry.
And in the meanwhile, I am sharing with the public the.
No. Sorry.
Yeah, don't worry. In the meantime, I am sharing with the public the PDF of the presentation, so you can download it.
Okay.
Give me a minute. Okay. So, people, you can ask all the questions you have, and in short time we are asking it.
Yeah. Sorry.
So, I'm now sharing with you the presentation. Please, if anybody has any problem downloading it, you can tell us. Should appears in the tab documents in a couple of minutes. Okay. Yeah. I think it is uploading. Yeah. So Raul, let's see if we have any questions. Okay.
Okay.
I'm sure we have. Okay, there are people asking for the presentation. I'm quite sure that it's already uploaded. So if any of you have problems, you can tell us. And we have some questions. Okay, Raul.
Okay.
The first question is what is the recommended air changes per hour while designing the ATEX system? I think you already explained the formula, no?
Well, yeah, we explained the formula, yeah, but in the standard it's not determined about if you need determined radio. So at least you can calculate it as the formula as a minimum airflow, and then you establish that, well, for this case we need 10 times the volume or 8 times or 8 times the airflow we calculated to have a higher dilution. That's it.
Okay, thank you. Let's see if we have any more questions. Let's give the people a couple of minutes, and if not, okay, you can reach both of us, Raul or myself, to answer any question you have. Okay. Okay, I think you did quite well, Raul, because we don't have any more questions. I'm sure the part of the marking is a little bit tricky, as Raul told you. So I recommend you to review the PDF, the presentation, in order to understand properly the mark, because it's. I think you did well explaining this.
Yeah, I explained details because it's very tricky, and also because we need two markings on the equipment, so it's hard, and you have to learn which are each part of the marking to know, to understand if this equipment suits you.
Too many factors to
Exactly.
bear in mind. So Raul, I think we don't have more questions. there are people writing and saying to you, thank you so much for your presentation. I agree with them. So thank you so much for being here. For you, the people that are with us today, thank you so much for being here. As you know, this is the last micro-learning of the year. We are coming back next year with more micro-learning, more interesting topic about ventilation systems. So see you in a couple of months. Okay. Thank you so much, Raul. See you. Bye bye.
Thank you, Carlos. Bye.
Bye.